In this video, we covered the working principle and showed two methods for making supercapacitors, also called ultracapacitors. In this animation, you can see that when supercapacitor is charged up to 3 volts, the blue anions gather to the positively charged surface of carbon on the left. Upon discharging, the anion and cation layers disappear. Many bioorganic materials can be converted to porous carbon by heating and activating procedures. Let's compare energy density of lithium-ion battery, supercapacitor and electrolytic capacitor. With the electrolytic capacitor, the LED light burns only a fraction of a second, and with the supercapacitor for 30 seconds, but the battery can keep the LED burning for half an hour. Thus, why we need supercapacitors at all if they last less than batteries? It is because of their power. It can heat up a metal rod until it starts melting and burning. Iron sponge starts glowing. This 3200 farad cell can be charged up to 2.8 volts. Measuring of current output was not easy. Even with this beast we got only 800 amps, after which the machine refused to measure further. However, the voltage of a single element is too small to show something spectacular. The sparks are quite small. Better performance can be achieved if several elements are connected in series. Here we measured 188 amps, but due to 6 volt output, much more impressive sparks were achieved. This supercapacitor assembly could be used in combination with lead-acid battery to help starting internal combustion engine at very cold temperatures.
Now, if you want to build a simple supercapacitor with household materials, first you need to find a metal mesh, which can be cut out from a pan oil trap. The electrode material for a supercapacitor is porous carbon. A widely available activated carbon from a water filter is made of coconut shells. Next, epoxy glue is mixed and activated carbon is poured on the current collector. After adding some more carbon, the metal plates are bolted and treated with a 20-ton hydraulic press. When the glue has hardened, the construction is opened and the electrodes are cleaned off the excess of carbon. Ordinary tissue paper serves here as the membrane. The stack is placed in a tic-tac box. Electrolyte is aqueous solution of sodium sulfate. Finally, the cover is fixed with a glue. Previously, we have made cells with sodium hydroxide, but this died quickly. Potassium hydroxide electrolyte gives somewhat higher stability, but clearly sodium sulfate electrolyte gives the best lifetime. Pseudocapacitors are supercapacitor types where some chemical reaction occurs. For example, here we have added manganese dioxide, which increases capacitance but reduces efficiency and power. If we would connect 10 1.2 volt cells in parallel, we would get 7000 farad supercapacitor. In case of series connection, we would get a 70 farad 12 volt supercapacitor.
Better carbon for a supercapacitor can be obtained when artificially made carbonaceous substances are used, such as carbides. To synthesize porous carbon, a carbide precursor is treated at high temperature with chlorine, which reacts with titanium and formed volatile titanium chloride is evaporated. Remaining porous carbon has optimal and very regularly sized pores, and thus such supercapacitor gives highest energy density. In this recipe, the fine carbon powder is mixed with Teflon binder, then the mass is kneaded between the fingers. Now we start to roll press the electrode into a thin sheet. After multiple rollings, a 150 micrometer thick electrode sheet is obtained. To increase electronic conductivity, the carbon sheet is inserted into the vacuum chamber and aluminum current collector is deposited onto the carbon. Next, I will cut out the electrodes. The membrane is cut out of a cellulose sheet. 2 electrodes and the membrane are assembled in a test cell, which is then tightened. Because of the electrolyte is moisture sensitive, we have to add it in a glove box. The glove box system contains a load lock, which is vacuumed to remove all air. Now the large gloves must be pulled on. Inside the glove box there is pure argon gas. The electrolyte consists of 3-ethyl methyl ammonium tetrafluoroborate salt in acetonitrile. The cell is filled with the electrolyte and closed airtightly. This supercapacitor can be charged up to 3 volts, which takes 10 seconds. It has enough power to spin a propeller for a few seconds. In commercial supercapacitors, the rolled layers of carbon sheets form a cylindrical shape. To measure capacitance, we use potentiostat. Cyclic voltammetry curves are nicely almost rectangular and indicate that indeed with organic electrolyte, the usable voltage is 2 to 3 times higher. Charge-discharge curves are almost linear for both capacitors, but notice how much faster the more advanced capacitor is. For example, supercapacitors can be used to help starting windmills or in combination with hydrogen fuel cells to stabilize high current spikes when hydrogen car or self-driving bus accelerates.